Hey folks, in Lesson 10 we'll be discussing the path frame. And the path frame is the second of our non-inertial reference frames. We did our polar frame, now we have a path frame. But one thing that's unique about the path frame is that we really don't care particularly about where the position of the point is or where the particle is in the path frame. This allows us to really focus in on the velocity and acceleration, and just like it says with a path frame, we're going to be defining this reference frame with respect to the path that the particle is traveling on. So let's start out simply by defining our reference frames. Always we have to define our inertial reference frame, and here we see the standard up and to the right axes that we've seen before. We'll call this E1 and E2, like what we've seen. And so our inertial reference frame, I, has an origin of O, and the basis vectors E1, E2, and E3. And so in this case, E3 is pointing out of the plane. And so we go through our standard definitions of that however we like to. So we'll say E1 pointing to the right, E3 out of the plane, and then E2 is E3 crossed with E1. So there's our inertial reference frame, like what we've done before. Now for our path frame, though, we need to base this upon our something that's on the path. We've said before that our velocity is always going to be tangent to the path. So this would be the velocity of point P, the velocity vector of point P in the inertial reference frame. And so we're going to put a unit vector in that direction that's going to define one of our axes. So this would be frame B. So B is going to have an origin at point P. So it's an origin on the particle. And we're going to have a unit vector that defines that direction, which is in the direction of the velocity, or tangent to the path, of E sub t. So it's a tangential unit vector. So our first vector is E sub t. Then we need another vector that's going to define an axis that's perpendicular to this. So our other axis will be, in this case, pointed down, and that's a special direction because it's always going to be pointed in the direction that's going toward the inside of the radius of curvature. And this would be E sub n. So a normal vector. So we have a tangent vector and we have a normal vector. So our second vector is E sub n. And then we're going to have another vector which we'll call E sub b. This is called the binormal vector. So when we define these unit vectors, E sub t is along the velocity vector, and then we have E sub n, and this is pointed to the inside of the curve. And then we have an E sub b. This is called the binormal vector. And then this is simply going to be E sub t crossed with E sub n. I'll put this here, binormal vector. All right, which really comes into play in 3D. So let's take a look at this reference frame that we've just defined with these three vectors, in which we have E sub t along the tangent. Hopefully that's very clear. E sub n is always pointed to the inside of the curve, and then this binormal vector, take a look at this, is that if we have an E sub t, which is always pointed in that direction, E sub n is pointed toward the inside of the curve, then that means that our binormal vector is going to be perpendicular to that, but it's not always going to be pointed inside the plane or pointing out of the plane or into the plane, but it's going to switch depending on what the radius of curvature is. So for example, here, if this is E sub t, then E sub n is pointed up. And that means that E sub b, which is E sub t cross E sub n, is going to be pointed out of the page when the particle is at that point. But the one that we just defined, in the blue, we have E sub t pointed to the right and E sub n pointed down. And because it's E sub t crossed with E sub n, you can see that here our binormal vector, is pointed into the page. So I recommend that you use an E sub b instead of an E sub 3 like they use in the book, because oftentimes, we define our inertial reference frame with an E sub 1, an E sub 2, and an E sub 3. And so as not to confuse this E sub 3 with an E sub b, with a third vector of the path frame, then let's just use E sub t, E sub n, and E sub b, and that way this binormal vector can flip as it needs to in and out of the plane. So now let's talk about these inertial kinematics that we can define using the path frame. Now, we're not really concerned about position, so let's just start with velocity. And so for our inertial velocity, v of p with respect to O, in the inertial reference frame, remember that we've defined this reference frame based on the direction of the velocity. So that means that our velocity is only going to be in one direction. It's going to be in the tangential direction. So that can be the magnitude of the velocity, v, multiplied times, or in the direction of, our tangential vector. Easy. So to find the acceleration, we simply differentiate this. So we're going to get acceleration of p with respect to O in the inertial reference frame. This is d dt in the inertial reference frame of v, velocity of p with respect to O in the inertial reference frame. And using our chain rule, we get v dot multiplied times E sub t plus v multiplied times the time differentiation in the inertial reference frame of the unit vector pointed in the tangential direction. Now we've already defined in this course that when we take the time derivative in the inertial reference frame, or any reference frame, of a unit vector, and so here we've got the time derivative in the inertial reference frame of the vector that's pointing in the tangential direction, this is going to be equal to the angular velocity of reference frame B as observed in reference frame I crossed with our unit vector. But one thing we haven't defined yet is what this is, the angular velocity of reference frame B with respect to I. Now here we've got this reference frame that's changing directions, remember? So we've got, there's our unit vectors, there's our unit vectors, there's our unit vectors, there's our unit vectors. And so we see that our reference frame is constantly rotating, but not just a single rotation, but changing orientation relative to our inertial reference frame the entire time. So what we need to do is we need to figure out what the instantaneous angular velocity is, because this is an angular velocity, but what the instantaneous angular velocity is at each of those times. And so here's how we'll do this. Let's zoom in on a section of this curve, we'll say right there, and then let's take a look at what exactly is changing within that curve. So if our point P is somewhere down here, then what we say is that anytime we're on a curve, that we can model this curve as if we were fitting a circle right to this point. And so here's our circle. The circle is going to have a center to it, and then we're only really concerned about this really small area right there, this really small arc length. And so on this path, this small arc length we'll call ds. So it's an infinitesimally small arc length. And then the circle has a center, and the circle has a radius, which we'll call the radius of curvature, that describes the radius along that really small arc length, and then we're defining this change in angle as a d theta. So this arc length is ds, and it's equal to the radius of curvature multiplied times d theta. Alright, move that up there. And so we rearrange, and we'll get d theta is equal to ds over the radius of curvature, r sub c. And if we divide both sides by dt, then we'll get d theta over dt is equal to ds dt multiplied times 1 over the radius of curvature, r sub c. So these are things that we recognize now. So d theta dt is actually equal to theta dot, and then ds dt is equal to s dot, or v, our speed. Okay. And so we can rewrite this now as theta dot is equal to our speed divided by the radius of curvature. And this is what's nice about having that binormal vector now. It's because this speed is always going to be in the e sub b direction, or the binormal direction. So we now have an expression for our omega b with respect to I, in which this angular velocity is going to be theta dot e sub b, where theta dot is defined as our speed divided by our radius of curvature. And so continuing with our derivation, we're going to get the time derivative of e sub t is equal to v divided by the radius of curvature, or speed divided by radius of curvature, in the binormal direction, cross with e sub t, which is going to give us our speed divided by radius of curvature in the normal direction. And then when we substitute this back in, we see that our acceleration of p with respect to O in the inertial reference frame is equal to v dot, or our acceleration, this is our increase in speed or decrease in speed in the tangential direction, plus our speed squared divided by the radius of curvature, and that's in the normal direction. And so we get this really nice, simple expression for our acceleration. We've already seen that our speed also gives us a nice expression, because it's going to, or our velocity is going to give us a nice expression, because it's our speed in the tangential direction. Our acceleration is going to be the time derivative of speed in the tangential direction, and then v squared divided by the radius of curvature in the normal direction. Now we've already spent some time looking in the polar frame at several different quantities that you should recognize here. So for instance, if we look at v dot in the tangential direction, this is actually equivalent to what would be a radius of curvature multiplied times theta double dot. So you should recognize that from the acceleration equation solved in the polar frame, in which this is in the e sub r direction. In addition, if we put this in terms of polar frame, this is equivalent to a radius of curvature multiplied times theta dot squared. Okay, we saw from that this is in the polar frame, and so we see that v squared over our radius of curvature, in which v squared is going to be our radius of curvature multiplied times theta dot squared divided by a radius of curvature, and so from this we get the radius of curvature theta dot squared, which is our centripetal acceleration. So it's our tangential acceleration and our centripetal acceleration that we've already seen in the polar frame. And a question that you should be asking yourself is that if I've got this path and I need to know the radius of curvature to be able to put this into the inertial acceleration in the path frame, how do I find the radius of curvature? Well, there's an equation that you need to have handy, and so that says that the radius of curvature is equal to, in the numerator, it's going to be 1 plus dy dx squared, and that entire quantity raised to the 3/2 power, and then divided by the absolute value of the second derivative, d squared y dx squared. And so this is saying that if we know a curve that's well defined in the x and y coordinates, so back in the Cartesian coordinates, then we can determine the radius of curvature at any time by knowing the first derivative and the second derivative of that particular curve. And so now, armed with this information, we can begin to solve problems using the path frame. And so let's work this example where we want to find out where a car is going to slide off the road. So the car is on a curve with a 300-meter radius. It's starting from rest, and it's going to speed up, or it's going to accelerate at 3 meters per second squared. And so in this case, speed is going to be the second derivative of position. And so if the coefficient of the static friction is 0.51 between the tires and the road, now we can determine when it's going to slide off, or how far it can make it around this curve. And so we have a radius of curvature of 300 meters. And our reference frames are going to be our inertial reference frame, which we can really place anywhere. Okay. As long as it is inertial. So E sub 1, E sub 2. And then we do need to define the reference frame on the car very well. And so in this case it's traveling clockwise, and so we have an axis here, and then we're going to have an axis pointing to the right. We chose these axes because this is going to be our tangential axis, and then we have our normal axis. Okay. Alright, so for reference frame I, we can make a point O. So O, E1, E2, and E3. Okay, we'll define those saying pointed to the right, pointed up, pointing out of the plane. And this is reference frame B. Reference frame B is going to be located at point P, which is where our car is. And we have a tangential vector, we have a normal vector, and then we have our binormal vector, okay, where our tangential vector is along the velocity vector. That's the inertial velocity vector, and our normal vector is always pointed inside the curve, and where our binormal vector is going to be equal to E sub t cross with E sub b. Alright, so as we look at this problem, we see that we're going to solve for how far around the curve the car can make it without slipping. So that means we need to put in an actual path coordinate in this case. So let's put in the coordinate s, okay, starting from this initial position. And so we see now that we can go ahead and back in our earlier chapter where we were doing integration, this is going to be s double dot is equal to 3 meters per second squared. And so we can integrate this, in which we get s dot is equal to 3t plus an initial s dot which we already know, it's starting from rest, so this is 0. And then so our position around the curve will be 3t squared divided by 2 plus our initial position. And we can set that equal to 0 too. Because remember, we don't really care about position. We only care about velocity or change in position when we're working with path coordinates. Alright, so let's take care of our kinematics now. So for the kinematics, we're looking for an acceleration because we're going to apply Newton's second law to this. And so our acceleration of point P in the inertial reference frame is equal to v dot in the tangential direction plus our speed squared divided by our radius of curvature in the normal direction. And so when we draw a diagram of this, here's our car, and here's our tangential direction, and then here's our normal direction as shown on our picture, then v dot is the same as s double dot, and v is the same as s dot, because that's our speed and our acceleration along that path. And so we get 3 in the tangential direction, and then we're going to get v squared over our radius of curvature, which is rc, in the normal direction, which is 3t squared divided by 300 meters in the normal direction. And then let's take a look at what we're really after here. And to do that, we're going to have to develop a free body diagram of the car. So for our free body diagram, we're going to draw our car. We're looking at it from the top. And so to get around the curve, remember that to stay on the curve, we've got to have constraint forces. And so in this case, our constraint forces are constraining our tires to the road, which means that in order to accelerate forward around the curve, we need to have a force that's pushing us forward, or constraining us from slipping backwards, if you want to think of it that way. And then in addition to that, we need to have another constraint force that's pushing us to the right on this car, which is going to create that curve. And so our force then is going to be a single force on the car that we can model as the components of these two directions. Well, that particular force is a friction force, because we're now talking about the tires slipping on the road. So the friction force has to be pointed in this direction. This is not Coulomb friction, this is static friction. And so our friction force model, rather, is equal to μs multiplied times the normal force. And so we know that this is going to be μs mg. And then putting this into our Newton's law, after we use our free body diagram, we get that our force, μs mg, is going to be equal to the mass of the car multiplied times the acceleration in the inertial reference frame. And because that we've modeled this as this friction force on one side, this is going to be the absolute value of that acceleration. And so we get this acceleration, this absolute value of the acceleration, simply by looking at the components here in the ET direction, the tangential direction, and the normal direction, and then finding out what that actual value is. And we do that using our application of Newton's law. We know that our static coefficient of friction is 0.51. Okay? We also see that we can cancel out our masses, and that gravity is equal to 9.81 meters per second squared, and this is going to be equal to the absolute value of our inertial acceleration of point P. And so when we solve for this, we get that the absolute value of our acceleration, or the magnitude of our acceleration, is equal to 5 meters per second squared. And what's convenient about that is that we can go back into our kinematics here and know that that's going to be the magnitude of this resultant acceleration. So there's our acceleration, our inertial acceleration of point P. And that absolute value of the inertial acceleration is equal to 5 meters per second squared. Now always look for simple ways to solve this, because you can use the Pythagorean theorem here, okay, and square these guys, add them up. But if you'll notice here, what we've got is we've got a triangle that has a leg of 3 and a leg of 5. And so if we have a leg of 3 and a hypotenuse of 5, that means this other leg is going to be a 4. So we can easily take this expression and say 3t squared I believe that's incorrect. I think it's 3t, the quantity squared. Let's get that right. So 3t quantity squared divided by 300 is equal to 4. And this gives us a time t that's equal to 11.55 seconds. And so we see now that if that's our max acceleration is 5 from our static friction, from our max force that can be added there, then when we plug this through, then we get that the car is going to slip at 11.55 seconds. Now back up to what our problem is asking for. It's not asking us for the time, but it's asking us for how far around the curve that the car can make it without slipping. Well, we have an expression here of the distance around the curve as a function of time, and so we'll use this and we'll say that S is equal to 3t squared divided by 2, and so we plug in 11.55 seconds, so S at t is equal to 11.55 seconds. Then we get 200 meters that the car makes it around the curve without slipping. Alright, that wraps it up for the path frame. So remember that the path frame is a non-inertial frame which has an origin at the particle, and which we've defined three new vectors, a tangential vector, a normal vector, and a binormal vector. Always have to set that up in detail every time, and that we use this when we're not particularly concerned about the position, but only about the velocity, acceleration, or a change in distance. All right, see you in class.